Maybe go to the video lectures. Okay, so today we will study Ethernet security. We'll start with one very basic concepts. Okay, and then we'll study one attack, which is CAM overflow attack. Okay, I know that many of you have not done layer 2 in your networking course. Okay, and I think one guest lecture was there. So what I have thought is that I will revise some concepts of Ethernet, and then we'll move on to different kind of attacks possible. Now you need to observe the patterns of attack. Attacks are very similar. Okay, including buffer overflow attack. That happens in practice. So just observe the pattern. We can apply same kind of pattern to higher layers as well, networking layer and transport layer. All right, so I've taken contents from all these sources, so please go through it. So we'll start with Ethernet concepts, frame, what is the structure of the frame, and then switch Ethernet. We'll look at some threads, and then one thread we'll take up in this class, and remaining we'll cover in the next class. Note the word frame, right? Frame and packet are used interchangeably. We use word frame when we are at link layer. Okay, layer 3 onwards, there's IP layer onwards, we use packet. These are just terminologies. You can use either one, it doesn't matter. But normally higher layers, we use packet. But you can also say packet in case of layer 2. Okay, so we'll revise the concepts of Ethernet. And please let me know if you don't understand anything. Now, Ethernet is connectionless. Okay, it means that there is no explicit connection between two endpoints. So there are, say, source and destination. Okay, when we create connection, then once connection is established, then we send series of packets of frames. Okay, so and first step, like we do it in case of TCP, first step is connection creation. Okay, connection creation in general, source and destination agree on certain parameters. Okay, and then they exchange number of packets, and then connection tear down. So basically there is a phase of connection setup, then data transfer, and then connection or disconnection. Okay, so same thing, connection oriented protocol, for example, that we use very often is, of course, TCP I mentioned, but also like when we make a phone call in regular PSTN phones. Okay, and when you make international call, you can see your call is progressing. It takes some time, right? When you call somebody, say in USA, it takes some time for call to be established, right? So that call establishment phase is nothing but connection creation. So basically you're signaling, signaling, the first phase is, of course, signaling, wherein a signal moves from one switch to another switch and reserves resources on the way. Okay, so when you make phone call, the path is fixed, and all the resources in between, like buffers and all that, are fixed or reserved for the call. It means that you are doing reservation of whatever computing resources you need end to end, including all the bandwidth on wires or Wi-Fi or sorry, wireless. The whole reservation is there, right? So that happens in PSTN phone. In TCP, of course, reservation is not there, but path I mean, basic parameters are fixed, and then packet exchanges can happen. Okay. All right. So there is no handshaking. Handshaking is essentially like SYN messages you say send in TCP, or in case of PST and SS7 protocol, the whole connection establishment between two endpoint that requires exchange of parameters and handshaking. Okay. So you understand now connection oriented and connectionless. So Ethernet is connectionless. It means that it doesn't establish connection. So if this is a destination address, it fills the data in frame, and then say this is a destination address, it writes, and also writes source address, and then fill the data and send it. That's it. Okay. In case, for example, in case of TCP, there is if the packet is lost, then the retransmission of packets happens, right? Here, in case of Ethernet, there is no retransmission of packets. So it does not, it means that the receiver will not acknowledge whether packet is received or not. Okay, so there is no acknowledgement or negative acknowledgement. Okay, on X on X. So whatever packet is received is just passed on to higher level, and just minimum checks are done. Like, I mean, we'll come to that. At the end, there is a cyclic redundancy code, which checks if there is 1 or maybe 2 bits are in error and so on, right? So these are error correcting codes that are there. So that's the minimal check is done. Okay, so whatever packet is received, it could be an error. After minimal check is done, it is passed on to higher layers. Okay. Okay. So what happens if the wrong, if the packet is in error or packet is missed, the packet may be lost. If this packet is in transmission is lost, and then this guy will not ask for the retransmission. So then how packet can be, but packet is important, right? When you're doing file transfer, files are very important. If even a single byte cannot be an error, right? So now, the assumption is that there is some end-to-end protocol that will take care of it, right? Okay, like TCP works on end-to-end. If required, this can work end-to-end. Yeah, the TCP will be used. Otherwise, UDP can be used. So many applications require reliable transmission. Then the TCP can be used. But large number of applications don't require reliable transmission, then UDP can be used. Then this perfectly fits into UDP model that you don't need reliability. Then okay, packet is missed, right? So why unnecessarily create retransmission here and increase the overhead? Okay. Any question? All right. Okay, there is a standardization available. You can read that. And of course, you know about CS513 with binary backoff protocol, right? So this is a basic protocol that's used. Is there anybody who does not know CS513? Is there anyone who has no understanding of CS513? Say yes. I mean, if you don't understand, I can spend a few minutes and explain you about it. All of you know it, then I will ask questions. Okay, then who can tell me? Okay, Gunjan, can you tell me what is CS513 protocol? How does it work? Yeah, are you there?
Yes, sir.
Yeah, tell me. You don't remember? Then you should have. Yeah, please.
CSMA wasn't covered in our networking course class.
Yeah, so you should have said no. Now when I'm asking question that do you understand it, you didn't say no. Okay,
Sorry,
please, yeah. So please ask questions. If it's good to ask. See, CSMACD name itself tells about the protocol, right? See, okay. Okay, so we'll start with this one. So, yeah, okay, so okay, it takes a while to recollect. Okay, all right. So carrier sense multiple access. Carrier sense. Carrier is what? Then sense multiple access collision detection protocol. Okay, so this is, so I will just tell you in very brief. So when Ethernet started, there was a thick Ethernet. Okay. There's a actually thick wire, that went in a building or in a lab from one end to another end. And then you will attach to this using transceiver your computer. And of course, there will be one interface, okay, which will run CSMACD protocol. So there will be multiple computers like this, okay, with Ethernet interface or Ethernet card. Okay, so like this. Okay, so this is how it started. Okay, now let's call it A, B, C, D. Okay, so now we use the same protocol that we use in the class. Okay, this class, for example, that when I am speaking, all of you are listening, and when I stop, then any one of you can speak. Okay, when I'm speaking, I'm A, for example, then the whole channel is available to me. Okay, and I am actually sending the frame, or I'm talking to C, and I will say in the beginning is for C, and all are listening, and then C will actually listen and grab it. Okay, all other will reject what's happening because it's not for them. So that's it. So when there is a gap, then you will start speaking, right? For example, D starts speaking when it finds out the channel is empty or nobody is speaking, we'll start sending it for B. Okay, he will create a frame with destination address B, source address D, and fill the data, and then put it on to this one. And then only B will receive it. All other will observe it but ignore it. Okay. Now this looks fine. What's the issue here? Issue here is that when two people start speaking simultaneously, when channel becomes free and two people suddenly thinks that channel is free and they start talking. Okay, it happens in class also. You are talking, I am talking simultaneously, or two of you can, if I ask question and two of you will start simultaneously, and there is a collision. Then what happens? One backs off, right? So here in the same thing, if there is this guy starts transmission and some other guy starts transmission, packet will traverse and then collide. Now when there is a collision, there is a change in signal, change in voltage value. Okay, and then this observed by all. All will observe that there is a collision. Okay, what will happen? In the class, as two people started together and there's a collision, they will back off for some time, right? And again see the silence and will start. Okay, so this way the protocol also works. When there's a collision, everyone will observe it and back off and then restart. Now if everyone backs off for the same time, then there will be another collision. And then everyone backs off at the same time and then restarts transmission, then there will be collision. Okay, so now the protocol says that it's a I mean the back off time should be different. and there is a period of back off, a maximum period, right? Within that, different nodes can randomly pick up a value and then back off for certain time. So probability of collision reduces for the second time. So that's as simple as that. This is CS513. Carrier sense, it means that each one station is sensing if there is a voltage or there's some communication going on. Okay. Multiple accesses, multiple nodes can observe that, okay, or sense that. And then if there is a collision, detect it. So this is a very simple protocol, CS513. And there are some, of course, limitation that what could be maximum length of the cable for collision detection. Okay, so these were the limitations. Because if this guy starts sending, only if this packet reaches end, okay, only then all will know that channel is busy. Okay, and then there will be some. And how does this know? Let's assume collision happen at this point at the end, collided signal will come back. Only then this guy will come to know there is a collision. So there is some how much time it will take for the node which is standing at the corner to know collision happened, depends on the length of this thing, speed of light, and many other factors, right? So I don't want to go into mathematics, but in general, there's limitation of maximum length. But nevertheless, so you understand CS513. So same protocol continues to be used. Okay, even now we are using CS513. Of course, there is no collision because we have moved from bus to star, which we'll discuss next. Okay, all right. Okay, so we were here. So benefits, all right. And Ethernet has become de facto. Earlier, there were many other technologies like token bus, token ring, and so on, but all gone. Okay, and now we have only Ethernet because Ethernet is extremely simple technology. Like we are talking, right? I mean, there's very simple protocol. Okay, and it's very easy to install and maintain. I mean, you don't need actually any expert to install the network at home, right? It's very simple. And it's very cheap, cheapest Ethernet switch will cost just few dollars. Okay. And it's scalable technology. I mean, you can start from 1 Mbps or even 1 kbps. Now, of course, now 1 kbps interfaces you won't get to a few gigabit per second. Now it has moved into hundreds of gigabits per second. Per port speed, per port I am talking about, right? So it's very scalable technology. And it has moved from shared media to switches. I mean, earlier we had something like this that we have discussed, right? There's a shared media and then connections are like this is shared media. Okay, so we have moved from that to switches. Okay, so a lot of things have, and then there is a change from electrical signaling to optical. Now we have optical Ethernets. So we don't have currents and voltages and so on. Instead of that, we have light pulses. Okay, so everything in Ethernet has changed as technology improved, but the frame format remained the same. Okay, and frame format is as follows. Okay, we have a payload. Payload is nothing but actual data that you want to send, right? And rest over all this is overhead. In order to send this data, you need so many bits. Similarly, this is overhead. Okay, this is useful data. Okay, now data can be filled here, and maximum data size is normal Ethernet frame up to 1500 bytes, and and the minimum size is something specified as 42. Okay, and then there are some special type of frames which can be as big as 8000 bytes. It's quite big, right? Okay, but in normal practice, we use this. All right. And then we have at the end CRC, cyclic redundancy check at the receiver. Okay, now there is no correction happening here. Okay, so you do the checksum of the packet and then find out there is something wrong. Okay, then you drop the packet. Of course, you know, some other protocols, of course, use error correcting code where 1 or 2 bits of error can be corrected, but Ethernet here does not. It just detection technology. There's something wrong, then just drop the packet. Okay, all right. Now apart from this payload, we have destination address and source address, and these are MAC addresses. These are 48-bit source and destination addresses, right? Okay. Okay, and then there's something called type field. Okay, type field is used, you know, suppose you are using IP, Internet Protocol data, because IP packet will sit inside. So how the receiver will know that data here corresponds to IP? It could be hundreds of protocols. The data can be corresponding to hundreds of protocols, right? So IP packet is sitting, that will come to know the type field will tell this is, there's some bit pattern will say that it's for IP. It could be for IPX, it could be some other protocol also, right? Because Ethernet is not was not designed only for IP, but today, because IP is very popular, then most of the time the traffic on Ethernet, or almost like 100% we can say, or close to 100, is only IP traffic. Okay, all right. So 48-bit source and destination address, and most of the frames that we Ethernet card that we get comes with address east into it. I mean, it's there. Okay, but of course you can program it nowadays. You can change it. All right. So and there are various types of addressing we can do. If it's all bits are 1, then it's a broadcast address. It means that when this frame is received, when frame is transmitted, switch will broadcast it to everyone. Or in case of thick Ethernet, if a machine is sending with destination address is FFFF, all 48 bits is 1, then every node will receive it. Okay, so that's broadcasting. Okay, it could be also a multicast. Multicast is basically a set of destination addresses, right? Okay, all right. We'll skip this. Our adapter is in promiscuous mode. Promiscuous mode is whether it silently receives a packet and is for observation of traffic. Okay, so it could be that. Addresses are globally unique when it comes from vendor. Okay, so there is a specific way of doing this, giving globally unique address. But of course, you can program it. Then there can be a clash of local or MAC addresses. It can happen if you program it wrongly. Okay, but it has to be globally unique. But this global uniqueness, we don't use it for global communication. Okay, so we don't, although Ethernet or MAC address of the machine that I have is different from your machine, but I am not using this your MAC address for routing of my packets. Okay, its significance is only within the local area network. All right. Now let's move to switch Ethernet, right? I mean, initially we had this kind of technology, thick Ethernet. Okay. Now there were problems of that. You know, I mean, first thing is that length is limited, and there are two collisions. Okay, we cannot do this kind of communication. This guy is communicating with this, and this guy is communicating with this. This kind of communication is not possible. Okay, so there are limitations of this kind. Bandwidth cannot be scaled here. So now what we did is that, of course, there in between there is technology called hub-based technology that came, but the technology that's used today is that has switches here in center. Okay, so what we have is that effectively same protocol can run, because if you just collapse it, right, then it's nothing but the bus, like the bus, right? The thick Ethernet one. You just collapse this, for example, this becomes a start topology. Okay, similarly here, so this is start topology. So CS513 protocol can be used. Okay. Okay. Now is a transparent to host. So host doesn't know that this switch exists at all. It knows that there are nodes like A, B, C, D. That's it. Okay. That's it. Okay. And it works in full duplex mode. It means that, for example, A and B are communicating with each other. A can communicate in one direction, or A to C, then A can communicate to C, and C can communicate to A simultaneously. Okay, this is called full duplex. Okay, and it's avoid collision. We'll see how. Okay, so what happens is this is a switch, and when A is sending it to C, it stores in a buffer, and when this port is available, it sends it there. Okay, so at the same time, when B may communicate with D, so B is sending a frame, which will get buffered here, and this switch will send it to D. So there is no collision happening here. All right. Okay, and then this switch just looks at destination and sends it there. Okay, but it has to know what port this destination MAC is there or connected. Okay, so now when we say that switch is transparent, is with the frames are never sent to switch address. This switch is transparent. It means that when A wants to send it to C, that it will not send it to first address of switch and then the switch will send, because that's not the way. It means that everything is, this switch for these nodes, this switch does not exist. It need not know. Okay. Now this switch is very simple switch, right? It has many connections. Like we have seen, 48 could be 1024 connection. How does it know that, say this, and each one has a MAC corresponding, is connected to node that has a MAC address. So say, let's see, MAC A, B, C, D, E, and so on. How does it know that this MAC B is connected to this port? It knows only about port. And let's say this port number 1, 2, 3, 4. Suppose B is sending it to E, and this is at E is at port 5. How does it know that E is at port 5? Okay. So what happens is that, like a policeman who's standing in front of, in the middle of, there are multiple houses around, and this policeman is new. And then how does it know that I live in a particular house and a friend lives in? So he observes it, right? He sees me coming out of, say, house number 1, then he knows I am here. Okay. So he notes it down. And when some visitor comes to him and say where Ravi lives, then he'll say that he lives in house number 1. Similar way is called self-learning. Same way switch learns where different nodes are connected, on which port nodes are connected, it will come to know about it, right, by self-learning. Okay. Now once it switch self-learns, it knows where different machines are connected, or MAC address or MAC cards are connected. Then it can simply forward the packet to that. There's no concept of broadcasting. Like in thick Ethernet, everything is broadcasted. If I'm node A sends it to node C, then it's broadcasted. Here, there's no need to broadcast, right? Because once this guy knows that if it's coming from A is going to C, it will buffer it, and then it knows the C is here. It's certain port, say port number, say 3. It just forwards the packet to port number 3. Simple. So there's no collision. Okay, all right. So, but it will require some kind of table which is called switch table. Okay, so there is a switch table. Wow. Okay. Each switch will have a switch table inside, which will have mapping between MAC address and port. Once this is known, then it can do the forwarding, right? So it's something like this. So now A is, now there are multiple ports here. So let's call it 1, 2, 3. Okay. Okay, just a minute. I missed. So this is port number 1, this is port number 2, port number 3, and port number 4. Okay. Now A has sent a frame for C. Now this guy will know, switch will know that the frame has come from A and it has come on port 1. So it will fill this information in the table, right? That A is at port 1. Okay. Now it doesn't know where C is, because it's just learning. Then it will broadcast it to all. Okay, and then C will read the frame, it knows its destination address corresponds to it, and then will accept that. So the one learning is happen, and when C responds, because then as part of higher level protocol, it may respond and will respond it for A, then this switch will learn that C exists at port 3. Okay, and it will look at the address, MAC address of A, search here in the table, and then it's found, then it forward the frame to this port, on this port, right? We'll just send the frame to this port. Okay, so protocol is then very simple. Okay, keep self-learning, and if you don't know where the destination is, just flood it. Okay, all right. So we can see it this way now. Okay, and there is something called time to live, because this mapping that we are creating cannot remain forever in the switch, because people can move from one port to another port. Machines can be moved. In that case, if machine moves after say a few seconds, then there can be and switch learns it for very long period of time, then packet will be sent to wrong port. Okay, so in order to avoid that, there is always a timer associated with the table, and then entries are deleted after a certain period of time, right? So we have table like this. We have MAC address, interface, and TTL. So now after receiving this frame, it knows that it has come from A, interface is 1, or port is 1, and TTL, time to live is 60. Okay, so if, and when C is not known, then its packet is sent to everyone. It's called flooding. All right. And the protocol is very simple then, that we have discussed so far. Okay. So when switch receives a frame, index the switch table using MAC destination, look at the MAC destination address, and create the table in a way that looking at the destination MAC address, you can directly reach to that particular entry, right? Okay, it can be a hash table kind of design or whatever. Okay, and it's a very efficient, intelligent design, such that searching time is minimum. So if you find the destination entry, then forward the frame. Very simple. To that, then okay, all right. If it's found, then forward the frame on that port. If it is destination is on the same port, okay, then drop the frame. So it's like this. There is a switch, and then 1, 2, 3, 4 ports, and these are A, B, C, D. If destination address is also A, now there's a possible, there's a possible that frame may have same destination address, or there may be multiple subsegments here and so on. There can be many reasons that if this guy is sending it to the one here, then packet is to be internally routed, but this somehow it comes here, then this will simply drop the frame, right? Because it is for internal consumption. If it is not, and if the entry is there, then it will forward to that particular port. If C, this table contains entry for C, if you look at this at port 3, it just forward. If it's not there, then just flood. So there's a protocol, okay, that we studied just now. Now we can connect these switches in hierarchy. This is one network, this is second LAN, third LAN, and they can be connected together. So we form tree here and can be very big. And this self-learning will continue in this also, right? The same algorithm we can apply to each, right? For example, if A is sending it to some node here, and this guy doesn't know where it is, the switch doesn't know where E is, it will flood to everywhere, and it will be, all nodes will drop it if it's not in destination. This guy also doesn't know, because network, whole, they all are in the cold state and just booted up, and there's no learning, so it will flood here and also here. And this guy doesn't know where E is, it will flood here. Okay, all right. So now there is no learning. When this guy responds, then learning will start. That E is here, so this guy will know that E is here. Then it, but it doesn't know destination address, then it will keep flooding, and so on, right? So when communication starts itself, the first time when A sends, this guy will know that A is connected to this port. Okay, when this guy forwards or broadcasts it, then this guy will know that A exists at this port. So right in the beginning, learning will start as follows, right? I mean, okay. Let's see. This is a table for 3 tables, and there's a table here also, because each switch will have a table. So when A sends it for E, okay, and initially all tables are empty, then this guy will know that A exists at port, say 1. Okay, when this floods everywhere, packet from A, then this switch will know that A exists at, let's say this also port 1. And the guy doesn't know where E is, it will again flood. And this guy will also know that A is at this port. What is this? It could be 1, 2, 3, 4, port 4, and so on, right? Whatever port it has received, it will know that that particular node is at that particular port, right? So each node will continue to learn this way, and when communication when E responds back, then again some other sets of node will know, and after some time there will be full learning, because ultimately, see why we have LAN, because LAN is because machines communicate with each other, right? So this is the basic concept. Now this, when we do flooding can cause problem. And one problem is that flooding can create loops. Okay, if we don't have tree structure, and if there is a, this kind of structure, there is a loop like this. This is a switch A, or switch 1, this switch 2. And when we say broadcast, they will continue to broadcast. So there will be flooding here. Okay. Okay, so flooding can lead to forwarding loop, right? Always, this will continuously forward the packet. Okay, and as a result of that, network will be totally choked. Okay, because when there's a broadcast and flooding, and then and there is a loop, They will continuously flood because they don't know where the destination address is. The end protocol says just send it to all, and this will continue to happen, right? So there is a protocol, very important protocol, which Radia, Pullman, and others have designed, is called that given one topology like this, how to find out spanning tree, a tree, such that there's no flooding, right? And now who can run this protocol? There is no networking. Generally, there is no some central controller or something like that, right? It means that all nodes have to run this protocol and distribute it. So this is a distributed protocol, distributed algorithm, and each node will run, spanning tree protocol to find out what links to activate and what links are redundant where the no communication happen. For example, now after running this protocol, they have found out this the tree, and all other protocols which are shown, all other links which are shown here are not activated. It means that no communication can happen on them. Okay, so I suggest you read this very important protocol called STP, spanning tree protocol. I think this would have been taught in your algo course anyway. So these are Cisco switches that you see, or this is TP-Link switch. This kind of switch you can buy it for just few dollars. Okay, now the question is what kind of threads it can have. Okay, any question up to this point? Are you able to understand Ethernet in concept? Are you able to visualize how does it work? Any doubt?
No, sir.
All right. Okay, now what kind of thread you can observe in this? Did we talk about security so far? No. Did we talk about reliability? No. So Ethernet is not designed for reliability because there is no retransmission, no error correction. Like, we have in TCP, we have sliding window and retransmission, etc. There's nothing happens here. Okay. Is there a security issue? Anything happens for security? No. It's designed, it's very simple, and says that you need reliability, go to high level protocols. My job is not to provide security. Similarly, security, I am not concerned about. Whatever comes to my port with destination address, I will just send it to appropriate port, outgoing port, right? That's it. So it's designed for functionality, efficiency, and flexibility. It's not designed for reliability and security. And this holes or these gaps can be exploited or have been exploited. So some of the attacks are CAM overflow attack. Now CAM is a content address memory. Table is designed using CAM. Okay, so basically content you search and efficiently you can search. Okay, this table, there's a content, basically normally addressing to memory is based on the address. Here, basically search doesn't happen by indexing to particular memory, but to the content. So it's very simple, and just forget about it. The whole idea is to do efficient searches. Okay, and then DHCP attack, ERP poisoning attack, VLAN hopping attack, and spanning tree protocol attack. So we'll study all these. I think spanning tree will skip because it requires at least one lecture to explain you what spanning tree is. And all kinds of threats are possible, like eavesdropping or sniffing attack. Somebody can passively listen to what's happening. Okay, wrong source and destination address. You can just send it to wrong destination address, right? You create some destination address and just send. Okay, and wrong source address. You pretend that it's coming from somebody else and then cause problem. And this kind of attacks can happen in case of IP as well. When we go to high level, we'll read that. Posing as someone else, just pose as somebody else and then send. Sending malicious frame with additional, change some fields and then send. And it can also disrupt the operation. Broadcast the message. You use destination address just all once and then flood the packet in the system, right? It will unnecessarily, it will choke the whole switch after some time. We can overflow the available buffer. And these buffers are there in table, switch table that we have just discussed now. And then find vulnerabilities in Ethernet, VLAN, DSCP, RP, etc. We'll study only few of these. So today, it's another 5-6 minutes, we'll look at CAM overflow attack. Okay, we know Ethernet is a 48-bit address. Okay, all that we know. And the table, switch table is called content address memory table, CAM table. Okay. And in switches, especially small switches that we buy, table size is fixed size. It can have only certain number of entries. Okay. All right. So let's look at this. Now this switch, aim is to overflow this switch. Okay, its table should be overflowed. And this guy, so now let's look at the normal behavior. So this is MAC A, MAC B, MAC C. Okay, now it has already learned that MAC A is at port 1 and MAC C is at port B. Okay, so now, okay, so what we are doing now? We are doing ARP for B. This guy says that where is B? I want to know MAC address of B. So it has IP address. Some IP address it has, and it wants to communicate to that, but it doesn't know the MAC address, because at layer 2, communication, when we look at Ethernet frame, we see that we need only MAC addresses, right? But it knows IP address. So IP address to Ethernet address, MAC address conversion has to happen. Now there is no conversion. There's no table that IP address, this IP address belongs to MAC, because IP address keep changing. So there's a protocol called ARP. Okay, so it will broadcast it to all that where is B with IP address, whatever, given IP address. And this guy will say that this is my IP address. Hence, I must respond back and will say that this is my MAC address. So when it reaches A, it will know that this IP address of B. So this is doing ARP for B. Okay, it's trying to find out, given one IP address of B, what is the MAC address, and then this guy doesn't know about B. B entry is not there, so it will send this packet to all. This normal operation, right? And then back will respond back that this is my MAC address, and then and it will send it to, because source address, that's this guy MAC, this guy A has sent it earlier, so it will send it back to A. So it will already be broadcasted, because this switch knows where A is, so it will come here. Now this learning has happened. So this is a normal operation that we have studied, right? Okay. So this is a normal. Now if A wants to communicate with B, so it will just form a packet, and then this guy has already learned where B is, and so it will communicate here. So this is a normal. Okay, now CAM size is fixed. Now this guy, if this guy is naughty, it can create different MAC addresses, because MAC address can be changed. Okay. Okay. So an attacker connected to switch port will flood the switch with very large number of Ethernet frame with fake MAC addresses. Okay. So now what will happen? Fake source addresses, right? It will call switch to XSM and flooding with network with all ports, right? So it's like this. Okay. So it will create different MAC addresses. So it's like this is switch, and it's connected with, okay, A. Actual MAC address is A. Okay, but this guy will send, and this there is a table here. Okay, and this port 1. So initially it sends its own address. So it will say A is at 1. Then within a few milliseconds, microseconds, it will change its port address to B, and send a packet to some destination address. This guy will put it B at 1, will change it to address to C, again 1, and this way, after some time, this table is full. Now, if some other guy say MAC address say F is sending, which is connected to at port say 3, sends a packet for say some address G, then this table is full. And when the search is done for G, there is no hit. So it means that now for G, this frame that's received here will be broadcasted to all. So it will flood. And this flooding will happen continuously. Okay, and it will cause, lot of traffic, and switch will not work function properly, right? Okay, and you can do this, you can experiment it with the Makov tool which is available. All right, and okay, so this we have studied. In order to control this, what we do is that we limit the number of MAC addresses per switch port. If we say that only at this port, only 3 MAC addresses are allowed, then there is no possibility of it, right? All right. So, of course, I mean, an attacker can create 3 MAC addresses, but that will not flood the switch because there are only few attackers, right? All right. So this is what the CAM overflow attack is. Please go to slide set. And this is what we have studied today, right? And we have studied about how switches work. We also looked at the concepts of CSMACD. Ethernet is not designed for security and reliability. So it's a responsibility of higher levels to take care of this, reliability, but security cannot be handled by higher layers, right? So switch developers have to think of some mechanism to provide security, because security now, there's the difference between security and reliability. Reliability can be taken care by TCP, etc. But security of Ethernet cannot be responsibility of higher layers, right? So we have studied today a particular attack called CAM overflow attack, and and there are some countermeasures for that. The switch manufacturer will not allow many MAC addresses per physical port. All right. Okay. Thank you. Any question? All right then. Thank you.